Okay, so this recording will be for the first part of Module 12. Module 12 deals with geometric optics. And I want to start by talking about the law of reflection. And that law simply states that the angle of reflection equals the angle of incidence. So when you have a beam of light striking a surface, so this would be the angle of incidence is the incoming light, and the angle of reflection is the reflected light or the outgoing light. And all this law states is that that the angle at which the light comes in will be equal to the angle at which the light will go out. So let's look here at a figure. Okay, so this shows so on the left side you see the angle, the incident ray, and then you see the reflected ray, and you notice that the angle of incidence is equal to the angle of reflection. So that's all that the law of reflection is. There are some practical applications to that. So we see things because light reflects off of an object and enters our eye, and then that sends a message to our brain, and it forms an image. So if we look at what happens in a mirror, so a mirror, this is a flat mirror, and so what happens in a mirror is that light shines on you from the light in the room, and then the light will bounce off of you, and some of it will, as that light bounces off of you, some of it will hit the mirror, and then it will reflect off of the mirror, and at certain angles, at a certain angle of incidence, the light will be reflected into your eyes. So that light that is reflected off of the mirror will cause you, it'll cause your brain to form an image. And then the other thing that you should notice is that the reflected light, so this reflected light that's coming off of the mirror into our eyes, it appears as if it's coming behind the mirror. And if light is reflected, if light is reflected off the mirror at numerous places, then you form a complete image. You see the complete image of your body, but it appears to come from behind the mirror. And so the brain will form an image where the light appears to have originated. So the light appears to originate from behind the mirror. And so we refer to this as a virtual image because it's formed by extrapolating these light beams, and if it's a flat mirror, the object that you see will be the same size as the object, and it will also be the same distance behind the mirror as the object is in front of the mirror. So if you're standing 3 feet in front of the mirror, the image that you see will appear to have come from 3 feet behind the mirror. So the beams of light that reflect are at the same angle that they hit the mirror, so that the image that you see is precisely opposite the object in the mirror. So it's the same size as the object itself, and it's as far behind the mirror as the object is away from the mirror. Okay, so that's how mirrors work, and you can see in this figure that the angle of incidence equals the angle of reflection. Okay, so that is what happens when you look in a flat mirror. However, not all mirrors that we have are flat mirrors. Some mirrors are spherical, and maybe some of you have probably had some experience with a magnifying mirror. So when you look in that mirror, the image that you see is magnified, and the reason that it is magnified is that it is a spherical mirror, so it's not a flat mirror, and instead the mirror curves away from the person who is looking at the mirror, and so the mirror curves away. So if you're looking in the mirror this way, the mirror curves away from you, and therefore it is called a concave mirror. Okay, so the mirror curves away from the person looking in the mirror. So in that situation, how does the angle of incidence equals the angle of reflection work in that situation? Well, here's what happens. If you have a concave mirror, the law of reflection says that the angle of incidence has to equal the angle of reflection. But how do you measure that angle? Well, or what is that angle measured relative to? So if we have this, we're going to have, the first thing you're going to have is you're going to have a tangent line to this curvature, and then there will be a line that is perpendicular to that tangent line, and the angle that is measured is measured relative to this perpendicular line. So the incoming beam of light is going to hit, so here's the incoming beam of light, is going to hit the curved mirror at a certain point, and then it is going to reflect out from that at a certain angle. This is not going to be drawn very well to scale, but the angle of incidence and the angle of reflection are measured relative to this line that is perpendicular to the tangent line. And then it is true that the angle of incidence is equal to the angle of reflection. And even though it may not look like that in my drawing, if you look at figure 12.2 in your book, you can see that the incoming beam of light and the reflected beam of light are the angle relative to the line that is perpendicular to the tangent, then the angle of incidence is equal to the angle of reflection. When light comes into a spherical mirror, the mirror will focus light toward a certain point, and that point is called the focal point. So any light beam that is traveling horizontal will be reflected through that focal point. So then the question becomes, well, what is the focal point? Well, the focal point depends on the curvature of the mirror. So a mirror that's like that, that's curved like that, is going to have a different focal point than one that's curved like that, or one that's curved like that. So the more curved the mirror is, the closer the focal point will be to the mirror. So this mirror is more curved, so the focal point would be closer to the mirror. One that's less curved, the focal point would be farther away. So we estimate we get the focal point by taking the radius of curvature of the mirror divided by 2. Okay, so the focal point is the radius of curvature, is half of the radius of curvature. Now, one thing to keep in mind is, so this spherical mirror, it's a sphere. So if we give the radius of curvature, then the focal point would be half of that distance. So it's the radius of the radius of curvature. So we are using spherical mirrors. However, one thing that you need to keep in mind is that in order for a curved mirror to focus light to a single focal point, the mirror really has to be a parabola. And your book has a picture of a parabola on page 390. So really, in order for a mirror to be able to focus light through a single focal point, it has to be a parabola. However, parabolic mirrors are very difficult and expensive to make. And so spherical mirrors are a close enough, they're a good enough approximation that we can use spherical mirrors instead of a parabolic mirror, and we can still basically get the same effect. Okay, so the focal point is the radius of curvature divided by 2. So it's half of the radius of curvature of the spherical mirror. Okay, so in order to determine what happens to light beams when they travel toward a mirror, we do something that is called ray tracings. Okay, so what we do in a ray tracing, so we make our concave mirror, and here's what we know about light that is traveling toward a mirror. First of all, to make a ray tracing, you're going to draw a line through the middle of that spherical mirror. And if we know where the focal point is, and we know the focal point if we know the radius of curvature of the mirror. Okay, so what we know about beams of light moving toward a mirror is that if a any light beam that travels horizontally, actually I'll make these different colors. So here's our mirror, here's our line that's through the middle, and we're just going to mark our focal point as there. Okay, and then let's change colors to blue. So any beam of light that comes into the mirror horizontally will be reflected off that mirror, and it will go through the focal point. Okay, and then any beam of light that goes through the focal point on the way into hitting the mirror will be reflected out horizontally. So if it goes in horizontally, it'll be reflected through the focal point. If that beam of light comes into the mirror and goes through the focal point on the way in, it's going to be reflected horizontally. Okay, so a beam of light coming into the mirror and passes through the focal point on the way in, it will be reflected horizontally. Okay, and then the last piece of information that we know is that any beam of light that travels through the radius of curvature will be reflected backwards along that same line. Okay, so hang on to that thought for now, but really the most important rules that you need to remember are that if a beam of light goes in horizontally, it's going to be reflected through the focal point. If it goes into the mirror and passes through the focal point on the way in, it will be reflected horizontally. Okay, so it goes in horizontally, reflects through the focal point, goes in through the focal point, reflects horizontally. Okay, so let's apply this then to a example. So we're going to look at example 12.1. Okay, so we have our concave mirror, and we have, that's really bad. So we have our concave mirror, and we have our line through the middle of that mirror. Okay, then example 12.1 says that an object is placed 20 centimeters from a concave spherical mirror that has a 10 centimeter radius of curvature. How will the object appear in the mirror? Okay, so first of all, we're told that the radius of curvature is 10 centimeters. So we can make a point for, and if you're doing this on paper, you can measure it out. I'm just going to estimate. So the radius of curvature is 10 centimeters, and so the focal point is half of that, right? It's radius divided by 2. So the focal point would be half of that distance, so it would be it would be there. And then we are told that the object is placed 20 centimeters away, so that's going to be about twice this distance. But if this is 10, then we go about here to place our object. And usually when we are placing an object, we just draw it as a vertical arrow. Okay, so this is 5 centimeters here. The distance between there and there, the distance between here and here is 10 centimeters. So this is all distances from the middle of the curvature. And then this is 20 centimeters away. Okay, so then if we apply what we know about how light beams reflect off of a concave mirror, we know that if the light beam goes in horizontally, it will strike that mirror and it will reflect out through the focal point. Okay, so in from the top of the object horizontally and will reflect through the focal point. Okay, then we'll use our blue marker to show that if the beam of light goes in and it goes through the focal point on the way in, it will strike that mirror and that will be reflected horizontally. Okay, and then the last bit of information is that if a beam of light goes through the radius of curvature on the way in, it will travel back out through that same through the same path. So the angle of incidence and the angle of reflection will both be 0. So that will go in and it'll come back out through the same path. I think adding 3 lines complicates things. So really we just need to look at 2 lines. And then what we look at is we look at where do the reflected lines intersect. Okay, so this red one went in here. So the red one came in here and it reflected out here. And then the blue one went through the focal point and it reflected out horizontally. So then we looked then at where do the 2 reflected beams of light intersect, and they intersect right here. Okay, and so at that point we would draw our image. We would so this is the bottom of the image. I mean, so remember our object is sitting here on the bottom. So this is the bottom, and now we see that the beam of light is going to be reflected here. So if this is the bottom, then this is the top. So the image that we see here would be upside down, so we would say it's inverted. And what about its size? It is smaller, so it's reduced compared to the real object that that was in front of the mirror. Okay, so this is the size of the true object. This is the size, this is the reflected image. It's upside down and it is smaller than the original image, than the real image. Okay, so that is one example of the type of how you can use a ray tracing to predict what an image will look like in a mirror depending on where that object is placed relative to the mirror, and also depending on what the mirror's radius of curvature is. Okay, now let's look at example 12.2. Okay, and example 12.2. So again, we're going to have a concave mirror. So we'll draw that line through the center of that concave mirror, and then this problem tells us that an object is placed 5 centimeters away, and the radius of curvature is 14 centimeters. Okay, so let's say this is R, so that's 14 centimeters away from the center of the mirror. So then the focal point will be half of that distance, so this will be F. That would be F, and so F would be 7 centimeters away from the center point. And then we are told that our object is actually placed 5 centimeters away. Okay, so here's our object. If that's 7, we'll make it like right here. So the object is going to be 5 centimeters away. Okay, so then we're going to do the same things as before. We're going to say what happens, what does the light look like, what would the image look like of this object in the mirror. Okay, so the first thing we would do is that any light that travels horizontally from that object into the mirror will reflect off through the focal point. Okay, so that's the first one. Then the second beam of light that we would look at is to say any beam of light that goes through the focal point will, before it strikes the mirror, will reflect out will reflect out horizontally. Okay, so obviously, since our object is in front of the focal point, the beam of light can't go through the focal point on the way to hitting the mirror, so we have to kind of extrapolate it out. So if that beam of light were going through the focal point before it hits the mirror, it would go like this. Okay, and then it's going to reflect out horizontally. Okay, so it goes in through the focal point, reflects out horizontally. And what we see from this is that the lines don't intersect. So what you have to do is you have to extrapolate those lines out. So where would those lines intersect? If we extract that horizontal line out like that, and if we extrapolate the line, the horizontal line went in and reflected out through the focal point. If we extrapolate that out here, then we see that these two lines intersect at that point there. Okay, so again, this is the bottom of our image. So the image that would be seen would be there. So this image would be upright, because its bottom, the bottom is at the bottom, and it would be, if we compare the size, it would be enlarged or magnified. This type of image where you have to, extrapolate the lines out for them to intersect is called a virtual image. So it's the type of image that you see in a mirror that appears to come from behind the mirror. The other one that we looked at, where the first problem that we looked at, where the lines actually do intersect in front of the mirror, that's called a real image. Okay, so virtual image is those that appears to come from behind. The image comes from behind the mirror, and a real image is where the lines intersect in front of the mirror, and the image does come from, we see the image from the inside of the mirror. Okay, so let's do on your own 12.1. Why don't you on your own 12.1. So in this problem, we are told that an object is placed 4.5 centimeters away from a concave spherical mirror that has a 12.0 centimeter radius of curvature. Draw a ray tracing diagram to illustrate how the image will appear in the mirror. Is it real or is it a virtual image? Is it upright or is it inverted? Is it magnified or is it reduced? Okay, so here's our concave mirror. We'll draw our line through the middle. And let's see, it says that the radius of curvature is 12 centimeters. So we'll say this is 12 centimeters. So that's R. And then F would be, the focal point would be half of that, so that would be 6 centimeters. And then it says our object is going to be placed 4.5. So we'll say that is 4.5, and we will draw our object there. Okay, so now we look at our beams of light. We'll start with the first one, in which any beam of light that goes in horizontally and hits that mirror is going to reflect back out through the focal point. Okay, and then we will do the next one in red, and that says that if a beam of light comes through the focal point, it'll be reflected out horizontally. And again, because this is in front, we can't exactly do it, but we can. So the beam of light would come in like this. And to extend my line for the mirror out here. Okay, so it's going to come in as if it came in through the focal point, and it's going to reflect out horizontally. Okay, those two lines don't intersect, so we have to extrapolate them back. So the horizontal one, the reflected line would be there, and for the one that came in horizontally and reflected through the focal point, it would be there. Okay, so this is the bottom of our image, and so that image is, this would be what the image would look like in the mirror. So it's, we would say it's upright. It's magnified, so if you look at the difference in the size, it's magnified. And it is a virtual image because the image is formed by extrapolating these lines. It'll appear as if the image comes behind the mirror. So that is on your own, 12.1. Let's go ahead and do on your own 12.2. And that one says that an object is placed 7.5 centimeters away from a concave spherical mirror that has a 12 centimeter radius of curvature. Draw a ray tracing diagram to illustrate how the image will appear. Is it real or virtual? Is it upright or inverted? And is it magnified or reduced? Okay, so again, we will draw our concave mirror with our line through the middle. Isn't really very well good through the middle. Let's do that again. Okay, that's better. And the radius of curvature is 12 centimeters. So if we say this is 12, so that's our 12 centimeters. So that means that the focal point is 6 centimeters, and our object is going to be 7.5 centimeters, so it will be right about there. So there will be our object. Okay. So then we look at the rays. If any beam of light that travels into the mirror horizontally will be reflected through the focal point, and then any beam of light that goes into the mirror through the focal point, so from this point on the top of the thing, if it goes through if it goes into the mirror through the focal point, then it will reflect out horizontally. Okay. I'm going to draw that again because I'm not. Okay, so in through the focal point will be reflected out horizontally. Okay. So then we look at where these two lines intersect. They intersect right there, right here. So this is the bottom of the image. So if this is the bottom, then the image that we see is going to be inverted. So this is the bottom, so this would be the top down here, and it would be magnified. And because the lines actually intersect in front of the mirror, it would be a real image. Okay, so inverted, magnified relative to this, to the real object, the image would be magnified and it would be a real image because the lines actually intersect. Okay, so that is, those are for a concave mirror. That's how you would do line tracings to be able to predict what an object will look like in the mirror. Okay, now you probably know that there is another type of mirror. So those were concave mirrors. There's another type of mirror called a convex mirror. And a convex mirror curves the other way. So now instead, so with a concave mirror, the mirror curves like that. In a convex mirror, the mirror is going to curve like this. And now what's different about these is that the object is going to be on the other side of the mirror. So when we do our ray tracings, the object, and so the radius of curvature for this type of mirror, the radius of curvature and the focal point are they're relative to this side of the mirror. So the object's going to be the light is going to off the object's going to reflect from this side, but the radius of curvature and the focal point is going to be on this side. Okay, so let's just look at an example. So we're going to look at example 11.3. Okay, so example 7.3 says that you're placing an object 14 centimeters away from a convex spherical mirror. Okay, so this is our object is going to be 14 centimeters away. And then we are told that the radius of curvature is 10 centimeters. So this would be our 10 centimeters. And so the focal point would be half of that distance. So that's f at 5 centimeters. Okay, so things are a little bit different now since the object is on the other side of the focal point. So again, it's still going to be true that an object, so you're going to use two lines. The first one is going to be the object that goes in horizontally and hits that mirror. And now it's going to reflect out as if it came through this focal point. Okay, so it's going to reflect out like that, as if it came through that focal point. Okay, that's the first one. And then the second one, which I'll draw in blue, will be a line that comes in to this object as if it is going to go through the focal point. So it's going to come in horizontally. I mean, it's going to come in as if it's going through that focal point. But when it hits the mirror, it's going to be reflected out horizontally. Okay? So it's going to go in as if it were going to go through the focal point, but it can't go through the focal point because it's going to hit that mirror and reflect back. Okay, so then we look at where do these lines intersect. Okay, so in order for us to, so again, we're going to have to extrapolate these out. So this would actually, the place where these two lines would intersect would be about right there. And I guess I didn't draw that great. Let me try to do this one again. Okay, so let's just try that again. We'll have our convex mirror. We'll draw our line through there, and we'll make this object 14 centimeters away, and this is 10 centimeters is R, and so half of that distance will be F. Okay, so then let's look at our two beams of light again. Okay, the first one will go in horizontally, And it's going to hit that mirror and it's going to be reflected out as if it came through this line. So it's going to hit there and reflect out there. And then it's going to go in as if it's going to go through, we'll go red. It's going to go in as if it's going to go through the focal point. So it's going in as if it were traveling through that focal point, but when it hits there, it's going to reflect out horizontally. Okay, so at the point at which it hits, it's going to reflect out horizontally. Okay, so then we have to look at where do the two reflected lines intersect. Okay, so there will be that one and this one, so they're going to intersect at about right there. Okay, actually, I mean, it'll actually be a little bit up there where they will intersect. So then this is the bottom of the image, this is the top of the image. So our image will be right here. So it will be upright. It will be reduced. And it will be a virtual image because it's formed by extrapolating the lines. It'll appear as if it came from behind the mirror. Okay, let's do on your own. 12.3. Okay, so an object is placed 2 centimeters from a convex spherical mirror that has a 6 centimeter radius of curvature. Okay, so here's our mirror. Oh, sorry, wrong way. Okay, it's a convex, so there's our mirror. And we'll draw our center line through, we'll draw our line through the center. And the object is placed 2 centimeters away, and the radius of curvature is 6. Okay, so we'll say that is the R. So F is half of that distance. And then the object, that's 3, we'll say this is 2. So the object is placed 2 centimeters away. Okay, so then we look at where our lines that come in, something that comes in horizontally will reflect out as if it came through the radius of curvature. Okay, so it's going to in like this and reflect out like that. And then if something comes in as if it were going through the line through the focal point, so it's going to come in as if it were coming through here, but when it hits that mirror, it's going to reflect horizontally. Okay, so again, those I have that one done. So those lines are not going to intersect with each other on this side of the mirror, so we have to extrapolate them out. So it came in horizontally, reflected out here. So we're looking at this line. In horizontally, reflected out. So we extrapolate that out. And this one came in as if it went through and it would have if we extrapolate it out, it would go that way. Let's draw this again. I'm not doing a very good job of drawing these. So the first one, here's our mirror, and our object is going to be, let's make it closer here. We have room to extrapolate these. So focal point is 3, the radius of curvature is 6, and so our object is going to be 2. So we will draw our object right there. Okay, so the first line, which we'll draw in red, the first line will go in horizontally, and it will reflect out as if it came through the focal point. Okay, that's the first one. Okay, then the second one will go in as if it were going to go through the focal point. So go in that direction as if it were going through the focal point, and it would reflect out horizontally. Okay, and those two do not intersect with each other, so we have to extrapolate that out, and extrapolate the red one out. So they would intersect at this point right here. Okay, so again, this is the bottom of the image, so the image would be upright. This is the bottom, so the image would be upright. It would be reduced, and it would be a virtual image because it appears as if it came from behind the mirror. Okay, so that is how we do our our ray tracings for a convex mirror. Basically the same procedure as for a concave mirror. It's just that the image is going to be, or the radius of curvature will be on the other side of the mirror compared to where the object is. Okay, the last thing we are going to do, and actually I think we'll stop because I don't think we really have enough time to get into the next topic, so we will stop there, and I would recommend that you work the problems in the back of the chapter. So you should be able to do problems 1 through 3 of the practice problems, being able to draw ray tracings for convex and concave mirrors, and then predicting what the image will look like.